Good morning, everybody, and thank you for joining us for this month's Scientists in Action Hidden Gems. You can tell because they're hidden. You can't see anything. Hide and seek.
All right.
My name is Amanda Abram. I'm one of the educator performers here at the museum. I am currently downstairs in the bowels of the museum with one of the coolest scientists here, and I don't even have to say that. I just know it. This is James Hagadorn. Before I turn it over to this guy right here, let's get a few housekeeping items out of the way. If you are one of our on-camera schools, awesome. Thank you for joining us. Thank you for being willing to do that for us. We are going to ask that you guys keep your microphones muted for the time being. When we are ready for your questions, we're going to call you out, and it's time to get your party started. We are going to ask, when you do ask your questions, come right up to the camera, state your name nice and loud, and your question nice and clear so that James can hear it well enough to answer that question for you. If you are not one of our on-camera schools, totally cool. Thank you for joining us. I want to get your answers, your questions answered too. So go ahead and type those into the chat, and I'm going to shout those out to James, and we'll try to get as many of those questions answered as possible. And with that, James, I'm going to turn it over to you. Why don't you tell them who you are, what you do, what happens down here, and I'm going to hop off camera.
Okay, bye. We'll see you up at the coffee shop. Well, thanks a lot, Amanda. Also, I just want to give a shout out. We've got a few other people helping to put this thing together behind the scenes. We've got Anna, we've got Riley upstairs, we've got Jess behind the camera, and Brandon over here. So just to give a big shout out to them. You might see Amanda and I most of the time, but this is a team operation, and we are here to turn you on to rocks, minerals, and who knows what else. So my name is James Hagadorn. I'm a scientist here at the museum. I'm a geologist by training. So what that means is I'm sort of like a detective in deep time. And I use different things like a detective does to understand how our planet operates both today, in deep time, and potentially in the future or in other places like on other planets. For me, the clues are rocks, minerals, meteorites, fossils, and structures that are all around us, many of which we can see today. I wanted to just sort of mention like where we are, and you notice this room is incredibly white. Don't you think we should do something about that? It's so boring. Let's go over here for a second. We have the world's greatest archival shower curtain right here, and we're 35 feet below the surface of the museum. So if you ever come to visit the museum, you'll be walking upstairs, but below you are rooms like this that are full of the archives of Earth and human history. And behind this fancy-dancy shower curtain here are a whole wide variety of specimens that record our planet's history. We've got giant pink crystals like this mangano-calcite here. We've got layered, dark-colored sedimentary rocks like this that have bits of coal in them from ancient swamps. We've got big pieces of metal like copper right here, in this case from Michigan. It's so heavy, I think, oh my gosh, that's 800 pounds. This is actually on a pallet, much like the ones you might see at giant big box stores or on a loading dock. And we've got meteorites and lots of other things. So these collections belong to you, the people. Oh my gosh, what's this one here? Anyone know this mineral? It's purple. It's really fun. It's amethyst. So, and it's a little pocket of itself. So we've got all sorts of different items here in the collections. And we use these items both to help explain how our planet operates through exhibits on the floor of the museum, through going to classrooms like yours, through broadcasts like this. And we also study them to understand our past. We've got lots of other cabinets full of materials over here on the left. And these cabinets have drawers and drawers and drawers of goodies in them. And what I hope to do with you today, with Amanda, is as you ask questions, is to pull items out, like this spotted rock right here, to try to answer questions that you might have about rocks, minerals, gems, and their friends. So you might ask, how did I end up at the museum here? Well, the short version is I took the stairs today because we're below the ground, quite a bit below the ground. But the longer version is I went to school like yourself, and I was a very curious kid. And I was always digging in the dirt and playing out in the yard or going into canyons or trying to go to the beach and pick up things and wondering how those things happen. And that sense of curiosity and wonder is something that we all have inside of us. And I think as scientists, like myself, we're all just pursuing that curiosity, and we're using different pieces of information to answer questions about things that we don't quite understand, or maybe as a society, we don't know how formed or how it happened. So that's a little bit about me. That's a little bit about where we are to sort of set the stage. And I think it might be time to sort of to hear from you. And we're going to do a practice run right now. We've got a survey queued up for you. And so Riley upstairs is going to queue up this survey. And I want to see what you think about collections. So this is a room full of collections. We have millions and millions of these objects here at the museum below ground. And we're holding on to these objects for you, the people. These are your collections, and we're the custodians at the museum. So why did we bother doing that?
Go ahead. There's a poll up on the screen for y'all. Go ahead and make your choice. We'll give you a little bit of time. And then James, when those results pop up, we'll let you know.
Okay. I know we've got some smart students online today, so let's see what they say.
I feel like we should have some music.
Yeah.
All right, there we are. The results are in, James, and 100% of the participants today said to study the history of the Earth.
Oh my gosh, I love it. We have deep time historians here. Well, it turns out the answer to that question was all of the above. We have collections for many different reasons. Some of our collections in the museum, including those from Earth Sciences, are here because they have cultural impact or impact for history. Some collections have great scientific value. Other collections have interest because they are just pretty. So you guys want to take a look at a couple examples of those? Okay, so when people ask me about museums, I talk about kind of collections in 4 categories, right? The 4 categories are things that are just pretty. You guys want to look at something pretty? All right, Jess, would it be better if I left this in the drawer or brought it forward? So this is a specimen. Anybody out there from Colorado? This is a specimen from just alongside Pikes Peak. And we've got a bunch of different minerals on here. This is an example of collections that are just here because of their aesthetic value, and maybe because of their educational value. These are big, smoky quartz crystals sticking up. This is a type of feldspar on here known as microcline, this kind of pinkish salmon-colored mineral. There's some cubes on here. That's fluorite. Fluorite is related to fluoride. It has the same element in it, and a couple of other things. And this rock is amazing, and I'm going to actually bring this a little bit over here because it's got big crystals growing on it. You can see them sparkle in the light. This is the type of collection we have just because it's pretty. And it's from Colorado. But this collection also, this item fits one other reason why we have collections, and that's because they're useful for teaching people stuff. And now I'm going to flip it over. Oh my God, isn't that gorgeous? I'm kidding. This has got to be the ugliest bottom of a rock I've seen today. This, if I were to polish it, is granite. It just looks like a countertop or maybe like a slab of rock that you've seen polished at a bank building or a library or on the pavement. And this is one of the most common minerals we see in giant mountains all around Colorado. It's granite. And what's interesting about this rock is that in this case, the side of the rock that you're looking at now, the crystals didn't have time to grow as they cooled out of underground lava or magma. And so they bumped into one another and they formed this interlocking array. I'm going to actually set this down right now, of crystals that you can't really see the shapes of the crystals really well. But the other side of the rock, there was a cavity open somewhere in that magma chamber or under the mountain that allowed these crystals to grow and get to their complete shape and form these amazing, what geologists call euhedral or pointy crystals. Sweet. So sometimes we have specimens because they're cool looking. Sometimes we have specimens in the collections because they have educational value. Sometimes we have specimens because they're of historic importance. And so oftentimes collections like this one right here, we've got a piece of an amazing crystal called Amazonite. And this is from a very historic location down near Glen Cove, which is sort of also near Pikes Peak. And it's a huge aqua-colored crystal. This is a mineral that we're kind of known for here in Colorado that forms as water vapor and radiation, to a lesser extent, impact the growth of this crystal deep underground. This, to a geologist, is actually a pretty ugly crystal. And so the reason we have this crystal is because it's of historic importance. It's from a special location. So that's another reason why we have collections. Compare that to, are you ready? Here we go. This one. Wow. Holy guacamole. Is that the most just amazing looking set of crystals you've ever seen? That's also Amazonite. It's unusual in that it has some interesting little stripes on it. It's got a couple of smoky quartz crystals sticking out of it and a bunch of other stuff in between. This is actually a very famous specimen. It's the logo for the Friends of Mineralogy in Colorado, a chapter or an organization of folks that have studied rocks and minerals for many, many years. So when we go back to this specimen here, you see why my eyes didn't pop out at the first one. Which one would you pick up first? Okay, anyways, enough about why we have collections. So we've got collections because of historic reasons, because they're pedagogically or educationally important, because they might be pretty. And then we also have things that are scientifically really useful and or industrially very useful. Let's find an example of one of those here. Let's see what we've got in here. Oh my gosh. Let's take a look at this bad boy. This is kaolinite, and it's a rock made up of tiny particles of clay. And it is a pretty drab-looking, ugly rock. And this rock is important for industrial reasons and for scientific reasons because those clays can tell us about ancient Earth and the climate that was there or the environments. But this rock is also important because we use these clays in lots of processes, from making bricks to using them in paint, to using them in lots of materials that you might find at your local hardware store or that are integrated into the infrastructure of our lives. But as far as being pretty, this is a fairly, in my opinion, drab looking rock. But it has good industrial and scientific importance. And so we have collections for those reasons too, because we're not just trying to collect the pretty stuff and archive it, but also things that are useful. All right, well, with that, I feel like I've chattered on enough. I imagine you all have some questions, and maybe we can go to some of those questions and then open some of the drawers in the collections here, or take a look at the racks and work together to try to answer them. How does that sound?
I think that sounds amazing, James. All right. We have Miss Rowland's class. You are all on camera. So if you want to go ahead and unmute, we'll take 3 questions from your group. So go ahead and unmute your mic. Come on up to the camera. State your name nice and loud and your question nice and clear so that James can hear it.
I'm Bella, and my question is, where do crystals get their color from?
Okay, the question is, where do crystals get their color from? Great question. The answer is, it depends. And I'm just kidding with that because it turns out in science there are a lot of different answers to the same question. So there are actually 7 different causes of color of rocks and minerals. And if it's okay with you, I want to tackle your question just about minerals, if that's all right. And so, because it turns out rocks get their color from the minerals that are in them or the other substances that are in them. A rock is typically made up of minerals or fossils or other grains, okay? So we're going to break that down into minerals and talk a little bit about those. The short version is that minerals get their color because of impurities in the mineral. So let's pick an example here. Okay, we're gonna roll down this aisle here. I showed you this mineral before. This mineral is manganocalcite. It is basically the same mineral as a clamshell. So it's got a carbon ingredient. Well, carbon is an element. It's got a calcium, and it's got a couple of oxygens all glued together, right? So this is basically the same mineral as a clamshell, calcite, but it turns out it has a little bit of manganese in it. And that manganese stains it pink. Just like when you put food coloring in frosting or you make Kool-Aid or something like that. Wow, what happens if I were to put a different ingredient or impurity into calcite? Let's cruise along here. Wow, Holy guacamole. Can you guys see this green rock here? Would it help if I pulled this out, Jess? Oh my God, that's really heavy. Maybe I'll slide it forward first. So this green mineral, malachite, oh boy, that's a big one, is pretty cool looking. And now this is a piece that's been polished, but this is the mineral malachite. You might see it in a lot of jewelry or things like that. It's also notable because it forms in caves, just like stalagmites and stalactites. It's also the same mineral as what you see in a clamshell, calcite or aragonite, except that it has a bunch of copper in it. And that copper causes it has a couple of coppers in it, in each atom, and it stains it green. Well, if we add a little bit more copper to it, maybe one more, maybe 3 pieces of copper, we get something that's beautiful blue, like this azurite specimen right here. So there's an example of one of the ways that we can change the color of minerals by changing the ingredients in the mineral itself. In this case, adding a little bit of copper, adding a lot of copper, or as in the example that was pink before, adding manganese. And those are all the different elements that make up the building blocks of minerals and, of course, our bodies and everything around us.
Awesome. That was a great question because I always question that too. So good question. Let's go ahead and get another one from Ms. Rowland's class.
Hi, I'm Alex, and I have a question for you. Do you have rocks from other planets?
Oh my gosh, do we have rocks from other planets? Indeed, we do. The nearest rock to another planet is actually in a cabinet way down the aisle down there, and I don't know that I could get it out really quickly. But can I get out a rock that is very similar to it that didn't come from Earth, but didn't necessarily come from another planet? Sound good? So let's pan over here on the right. And Jess, I don't know if it'd be easier to pan to the ones on the bottom or to that specimen up there. So these big brown-shaped blobs here are what are called meteorites. And meteorites are basically rocks from outer space that have fallen to the surface of the Earth. And one of the neat things about meteorites is that meteorites, first of all, they can be just like Earth rocks. They can be rocky, but a small portion of them are metallic. And I'm going to go get a prop for just a second. We're going to focus in on that one right there. So this important scientific tool, it's a magnet. Whoa, did you guys hear that? So this is what's known as a nickel iron meteorite. So this is a meteorite that is full of metal. In fact, it's mostly metal, like this shelf. And it formed, billions of years ago at about the same time the Earth formed. And it was either, as the planets were congealing around the sun, a lot of the debris from those planets, some of it congealed or merged into the planets themselves, and some of it was left surrounding the planet like in rings or sometimes as moons. Other parts of the debris of that early solar system formation ended up in a belt. Sometimes we've heard of the asteroid belt, right? And meteorites are just pieces of debris, whether they be from outside the planet or from the asteroid belt, or that are just careening around the solar system that make our way to the planet and fall to the surface because they get pulled in by our gravity. And meteorites, you've all seen one fall. You ever seen a shooting star? That's a sand to pea-sized piece or meteorite that's falling into the surface of the Earth and is burning up at thousands of miles an hour as it enters the atmosphere. Well, the bigger pieces don't completely burn up. They get kind of melted. They develop this sculpted crust on them called a fusion crust, often with little ice cream scoop shaped structures in them called remiglyphs. And they fall to the surface of the Earth. They might explode. And in fact, if you're out in the Western US, you can go see a meteor crater down in Arizona. There's a park there called Meteor Crater or Beringer Crater that you can go visit with your family on vacation or on a school field trip. That would be a great thing to do. Let's do a museum trip too. And you can actually climb into the crater that was formed as a meteor hit it. And many of the meteors that you see back here are the debris from that large collision down in Arizona. And if we can zoom in on this piece right here, one of the cool things about meteors is that many of them come from other planets. or from debris that's was out in outer space, right? So there are information about places that is hard to get to on Earth that you can only get to with a spacecraft. If you look at the crisscross pattern in here, this is called a Widmanstätten pattern, and it's only formed as that mineral forms under super high pressure and super high temperature, like what you see at the core of the planet itself. And unfortunately, unless you're Jules Verne or Bruce Willis or on some sci-fi channel, we can't actually go to the core of our planet ourselves as scientists. And so meteors are a cool way to get information, not just about other planets, but about places like the inside of our planet that formed billions of years ago.
Awesome. Ms. Rowland, let's get one more question from you all, and then I'll take some questions from the chat. We've got some really good ones coming in.
Yeah, and if you want me to answer these questions a little shorter or go longer, just give me the wave, because we're just having fun and exploring rocks and minerals while we're answering questions. Great questions.
And my question is, how do you know what time period the rocks come from?
How do we know what time period the rocks come from? Oh my gosh. Are you trying to get me to talk about my favorite mineral? I knew it. Love it. Okay, so turns out to figure out what time period the rocks came from, here's a quiz. What are the time periods, right? So Earth, oh boy, this is a two-part question. So Earth has a bunch of time periods. Some of you have heard the Jurassic, maybe. Some of you have heard of maybe the Cretaceous or the Pleistocene as periods of time when there were ice ages like in the Pleistocene or Ice Age time, or maybe the Jurassic was a time when dinosaurs cruised around. Well, it turns out that kind of like we divide up the year into months, right? Like, when is your birthday? My birthday is in August, right? And I don't tell people that my birth date is day 273, right? Or day 192. I break the year up into little chunks, into 12 chunks. That's what we've done, at least here by convention. And we break it into the month and then the day. And then some people even break it down into the time if they're really specific about things. So geologists do the same thing. We break up the time scale into these relative time periods like the Cambrian, Ordovician, Silurian, Devonian, Carboniferous, blah, 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 Pennsylvanian, Permian. It goes on. But one of the ways we do that is we figured that out based on the layering of the rocks on Earth. And this is actually there's an example right over here of a layered sedimentary rock, and you can see the layers in it right here. And so each of these layers was deposited one on top of another. The oldest layer is at the bottom. The youngest layer is on the top. And so we have divided the many, many miles of rock record that exist on Earth, which are now in little pieces, into different time periods. And what we've done is we've dated minerals that are in those layers to figure out their numerical age, right? Because a mineral might have elements in it that decay, that act like, very much like a clock. And those minerals, we can measure the amount of one element like uranium or another element like lead relative to one another and calculate the numerical age of the rock, saying, for example, that the Jurassic was 190 million years ago versus the Cambrian period, which was 500 million years ago. So we use a combination of the layering, we divide the Earth up into time periods, and then we measure the dates in those time periods using radioactive bearing minerals in those layers. Great question.
Great questions, French American School. Thank you for those. Let's take a couple from the chats. We have some questions coming in from St. Mary's Academy.
I know someone at St. Mary's Academy.
Oh,
named Stella Hagadorn.
Look at that. Connections are being made all over the place. I love this. They want to know, where do you find most of your good rocks?
Well, most of my good rocks come from the surface of the Earth. So that's a big thing. But it turns out that Colorado is an amazing place for rocks. And it's partly an amazing place for rocks because mountains have lifted up the rocks to the surface through the collision of two continents with one another, creating a crumple zone, if you will. We also have volcanoes that have lifted rocks up and created rocks here in Colorado. And it turns out that a lot of eastern Colorado and portions of Colorado are pretty dry. So we don't have a lot of soil and huge forests and swamps and things covering the rocks today, which allows us to see them. we also get to see those rocks when we cut through them, making roads or buildings or railways or things like that. So that's the short answer to that question, is we get them from all over. Yeah, I'm gonna go to the next question, but
Yeah,
let's talk about some cool rocks from Colorado in a minute. How does
Yeah,
that sound?
I think to tag on to that, how many different rocks are there at the museum?
Different rocks. The short answer is
Testing you
I don't
today.
know how many different rocks there are. We have about, I want to say about 1,000 rocks in our collection here. And then we have about somewhere over 50,000 minerals in our collection, which also all occur in rocks. And then if you want to really interpret things broadly, we have about, I want to say 500,000 or 1 million fossils in the museum. And those, most of those are in rocks. So the answer is a lot. And if you guys want to see a couple of examples of those, we could do that. That might be fun. So do you guys all know what a rock? Hey, let's do rock 101. So let's talk about rocks and minerals first. So and why don't we use some examples, and then that'll be fun because we can get to that answer to your question of why we have so many. So a mineral is basically a naturally occurring substance that has a specific composition and a regular structure. And that structure might, just open up a cabinet here and see what's in here. That structure might end up in it forming a really cool crystal like this calcite right here, right? And that structure has represents the way the atoms are arranged, kind of like a Rubik's cube or ball bearings internally. And so rocks are made out of minerals like that. And there are different kinds of rocks. I showed you a beautiful piece of granite before. Here's a really ugly piece of granite from Pikes Peak. It's full of little mineral crystals, little black crystals like pyroxene or biotite or feldspar or quartz. So rocks are aggregations of minerals and other substances. But it turns out that rocks are there's actually 3 kinds of rocks. There's rocks that are crystalline like this. There are also rocks that are sedimentary, that when this rock breaks down into little particles, be they sand or gravel, that those particles roll downhill and they may build up in a lake or on the side of a river or in a stream or at the bottom of the ocean. And all these little particles, which are now rounded, might aggregate or collect to one another and form a sedimentary rock. And we actually saw that layered sedimentary rock earlier when we were talking about time. In that case, those particles are really small, so they're harder to see. These are giant ball bearing-like particles, so they're a little easier to see. So these are examples of rocks that are sedimentary. When we squish those together, we can alter them and squeeze them into something else entirely, like a metamorphic rock. This is a fun one to think about. This is one from the canyons of Colorado. And actually, most of you, including St. Mary's, has this rock and the museum outside as landscaping stone. This is called a gneiss, G-N-E-I-S-S. And it is a rock that basically is like what would happen if you took this rock over here and you squeezed it under high pressure and temperature, like when mountains collide. And maybe you cooked it a little bit like when a volcano went by and altered its nice layers into what's called a schist or a gneiss, right? And in this case, what's happened here is this little squiggly line that looks like a worm is actually granite. It's the same rock type. Here, I'm going to try to, Jess, sorry for the pan. It's the same rock type as what we saw right up here. That's the same stuff, but this was a vein of granite that crossed this rock. And you're thinking, well, my veins aren't quite as squiggly like that, although my grandpa's are, right? Well, that vein was once straight, and it got squished under high pressures and temperatures and squished like taffy into a snake-like band that formed later on. And so that's why we call this a metamorphic rock, because it's altered, like a butterfly or a caterpillar undergoes metamorphosis. It changes Its composition is the same and its ingredients, but they're arranged in different ways. So that's the third rock type. You might see this all over Colorado. And so rocks are made of particles. They can be cooked, they can be sedimentary, they can be particles, they can be big crystals, but they can also be something pretty fun. Let's see, I got a couple examples here. They can also be particles that were grown, because minerals form in 3 different ways. Minerals form by cooling out of a melt, like rock from surface lava or underground lava. They form by getting squeezed. They can form by also growing in tissues. So you're growing minerals right now. You're growing the mineral apatite in your teeth and bones, right? Clams grow minerals, trilobites. Anyways, these are all part of our collections. These are fossils, but they're in rocks. All right, let's do another question.
All right, James, I'm going to give you a couple from,
Hit me.
let's see, Palmer Lake Elementary has been dropping some questions in the chat, question bomb in the chat, and I love it. They have questions about your particular job. So what tools do you use to find rocks?
Mostly I use my eyeballs. I use a geologic map. So maps are, geologists have maps that show them where rocks of different ages are on the Earth. And they look very similar to the type of map you might see on a road map, but they're colored slightly differently. So that's the primary tool we use to sort of start looking. And we might use satellite images to help us. And then we go out in the field and actually look at them on foot. Occasionally, you might have people that are doing marine geology and looking underneath the bottom of the ocean in submersibles or with ships or remote vehicles. You might also see that in lakes. Or very commonly, people perforate the surface of the Earth with a drill bit and they take cores below the surface to get a sense of what's there. So there's lots of different ways we use or approaches we use to find rocks. But one of the most common things you'll see a geologist use, and I had this on earlier, I didn't put it on around my neck, but is a hand lens. You see most geologists have a hand lens, and that's to get up close and look at minerals or the composition or the grains of a rock or a mineral and learn more about it. So we use tools from high tech to low tech and all different spatial scales to do that.
All right, James, they want to know, tell us about the most dangerous experience you've had while rock finding. This one intrigues me.
Okay, which one? So I'd have to say that, my most dangerous experience by doing field work. Boy, there's definitely a top 5 list, but coming up with just one. I would say the one that is the most memorable, but may not have actually been the most dangerous, was when I was out in the field and I was climbing up, and I was out here and I go up like this to the next layer of rock, and I'm coming up like this and I look up and there's a snake going right here, right in my face, right next to my hand. And it reminded me of something that my dad once told me. And he's like, don't put your hands in places you can't see where they are. And I thought about that afterwards, and I thought that was really good advice, Dad. But at the time, I was climbing, I was reaching up to get a purchase on something, to then go up to look at something, and just by chance happened to be a big old snake there. So, and it went, and I went, adios. The other one was a snake one too. And now I have had a lot of snake things in the field. As I was walking on, let's see, Paleta Folds in California, and hiking back, and I was walking along, and it was kind of dusk. And as I stepped midway through, I saw this circular rock between my legs, but it wasn't a circular rock. It was a coiled snake that was sleeping. Again, a rattlesnake. It was pretty cold, so maybe it was literally just chilling out, but I did the quickest hop I've ever done and just kept going. So we've all had things like that. So
it sounds like, if you've seen How to Train Your Dragon, where they talk about being Vikings and it's an occupational hazard, dragons, like snakes must be the occupational hazard for geologists.
Yeah, I think, or falling or twisting your ankle or who knows what.
Yeah.
But
all right, James, we've got a lot of questions coming in about colors, which might actually bleed well into.
All right, you guys want to see some cool colors? So it turns out not all of the really cool colors of rocks you can see. And hit me with a couple of the color questions, Amanda, while I close up this cabinet and open up another one.
Sure, let's see. How can copper change the color of a mineral?
So copper can change it in the same way that if you've seen a copper pipe or a copper roof and it rusts or it oxidizes, it turns green, right? Well, guess what? We just looked at a green mineral over there. Copper is effectively undergoing a comparable process. One of the things about color, I mentioned there's lots of different causes of color. There can be causes because of the structure of the rock. In other words, the way the atoms are arranged. There can be causes because of the way it absorbs the energy of incoming light and then reflects it or refracts it, that is, bends it or allows it to transmit. There could be causes of color because of the different ingredients. And one of the things that might be fun to do is maybe we can turn off the lights. And do you guys want to see some minerals that have different colors? And I'll give a shout out to turn off the lights in just a minute. But I want you to look at some specimens in the drawers here real quick to get started. So here's a drawer full of fluorite. And, you can see there's big crystals on it. It's kind of clear, yellowish in color, kind of light grays, lots of different colors of fluorite here. Here's a drawer full of other minerals. We've got a big white feldspar here. It's a beautiful crystal. We've got some schorl. We've got some benitoite. Here's a radioactive mineral. Zip, 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 zip. We had a Geiger counter. Don't happen to have one. That's andersonite. We've got some franklinite and calcite. We've got, hey, more calcite. We've seen calcite before, clamshell mineral. We've also got, these look like stones on the side of a lake, right? A river? Well, guess what? These are from the side of a river. These are from the side of Lake Michigan. So these are stones that have been battered by waves around it, and they're rocks that have minerals in them. They're kind of gray, right? So now we've seen what these look like under the light that we can see, but it turns out there's a spectrum of light of different colors, and these things, some of them absorb the light in different ways and then let off a different wavelength of light afterwards. So we're going to turn on a ultraviolet lamp. If we could turn off the lights, that'd be great. Thank you. And we're going to light these puppies up. So, holy guacamole. Wow. And I'm just going to put my hand in here for context. I am now showing these to you under shortwave radiation. So this is light that you can't see with your naked eye, but it's the kind of light that many of us put sunscreen on for. You can actually see in this huge feldspar, there are zones where there are parts of the crystal that are kicking out a greenish tint. That was a white mineral we saw before. This one, this radioactive mineral that kind of looked bleh. Man, that's so bright it would make Homer Simpson proud. And we all know he loves radioactive stuff, right? Here's a drawer full of minerals. This one on the end right here is one of my favorites. This is halite. This mineral was clear when we looked at it before. That's the same mineral that's in your table salt, halite. The calcite that we see here, it was so drab looking, is now a beautiful kind of whitish purple. And what's amazing about some of these minerals is that they will actually take up some of the energy that I'm imparting to them through this light. And I'm going to turn the light off now. You ready? They will luminesce on their own. Holy smokes. Some of these luminesce under a different wavelength. Let's look at these. I don't know if you can see these. These are these really ordinary looking gray beach rocks from Michigan known as euperlites. And that orangish mineral in there is sodalite. And so there are lots of different causes of color and even color that we can't see. Some of these crystals have secret color centers in them, like this one right here, which I'm going to now take the light off of. Oop, doesn't hold it quite as well. So I'm showing this under long wave radiation. It's coming out with a beautiful pink. Anyways, we could turn the lights back on. Hopefully that's fun. Does that get to some questions about color?
I think it does. Yes. And
So-
actually, we have about 5 minutes left.
Mm.
So I want to get a question to you because I think it's a nice wrap up and ties into the conclusion here from, let's see, Armstrong Academy. They want to know what professions involve geology.
What professions involve geology? Lots of them. People that look for water, people that, there are professions that look for natural hazards. So we have a team here in Colorado that looks for landslides on the sides of highways as the highways go through the mountains, and that figure out the geology of the ground that highways and roads and houses are built on. And those are called hazards that are, or geohazards. So we've got folks that work on those types of things. We have folks that help us find water underground that we drink or that we use to irrigate our crops. In geology, we have people that look for natural resources like oil and gas that need geology, or that are looking for helium, or that are looking for different types of metals that we need, whether they be molybdenum or gold or silver. We should look at some gold or silver, right, while we're here. I mean, we haven't looked at any gold or silver. Do we still have any gold or silver in here? I think so. Where do we have some gold or silver? I feel like we just had a piece in here a minute ago. We do some rumbling around. Oh yeah, here's a good piece. So we have folks, geologists that look for, here, let's just break out a couple of really sweet pieces of gold and silver. So this is a big silver vein from Creede, Colorado, Southwest. This is a big gold vein from Iderado, Colorado. These are kind of like a bread slice. These are slices through one of the veins of gold and silver. So geologists are involved in finding metals that we need for jewelry, metals that you need for your car, metals that you need for a battery. They're finding clays that you need for paint. They're finding the stuff you need in your toothpaste that you use to make your watch and your shoes. And by the way, what about all of the concrete in the world that is used to bake your building and the roads and your school? Geologists are helping with that too. Geologists help understand how climate works. Geologists help underpin meteorology in that sense, both ancient and present. Geologists work in deep time. Geologists work on studying how other planets form or are working and whether they're similar to ours or not. Gosh, I feel like I could keep talking about this for 10 more minutes. But as a scientist, geologists work with earthquakes. I mean, geologists work in so many different realms as scientists. And I think the same could probably be said is true for chemists and physicists and biologists. I mean, science is a very interdisciplinary enterprise, and rarely do you just have one person doing the work. You have a team of people, just like we have a team of people putting together this broadcast that works together collaboratively to understand how things happen, or to look for resources or processes that will be helpful to us as a society or as a civilization.
All right. And with that, James, it's time to wrap it up. Do you have any parting words for kiddos who might want to get into geology or something that inspired you that may also trigger with them?
I do. Would you be willing to hold on to a really amazing piece of gold?
Twitch
Amanda,
my arm.
twitch your- this is a 1-inch diameter vein of gold, just for like, geologists rarely see those. That's an incredible piece of gold from Colorado, donated to the museum, part of our and your collections. So I guess my parting words would be, pursue your curiosity, ask questions like this, because sooner or later you're going to ask a question that the answer is, I don't know, or we don't know, but we could potentially figure that out. And that's what scientists do. Science is about being wrong. Science is a verb, it's a process. And in each one of us is that process of asking questions and being curious. And so I would say just keep pursuing your curiosity, whether it's in nature, whether it's in a lab, whether it's just in the natural world or in your everyday happenings or things that you read. Because when you notice something that seems odd or unusual, chances are it is odd and it's unusual, or it's a gap in our knowledge. And that's what we as scientists pursue. And I think every kid, whether they're 2 years old, or every adult, whether they're 102 years old, has the potential to ask those kinds of questions. And if not, pursue them themselves, to maybe collaborate with a bunch of other people to do the same.
I like that. Science is a verb. That's
Science is a verb.
good phrase. Science is
Yeah.
a verb, guys. Go sciencing. All right. And with that, we had tons of questions that we didn't get to, but it sounds like it's a good opportunity for you all to science and try and find the answers to those questions that you put in the chat for us. And with that, that wraps up Hidden Gems, but join us next month for our next Scientists in Action. It's on May 22nd, the demise of the dinosaurs and expansion of mammals. should be a pretty good one. So hopefully we'll see you guys next month. Thank you again. Have a great day. I'm gonna hold this gold.
Take care. Thank you, Amanda.